He said yesterday that we have a quiz today.
What?
No, what?
No, not in your
Oh.
class.
Oh, not in my class. Okay. You bet.
What?
I actually didn't hear that you had a quiz.
All right.
Who did this, David? Is it really that deep? I don't think he's gonna care if I spell his name wrong to the teacher. I think Mr. Nash can put his name in it.
Yeah, but a lot of times when he does, he gets 5.
You're hilarious.
Thank you. I like picking on Mr. Nast. It's very easy. And he's actually fairly easygoing, so he doesn't come and try to kill me. All right. So let's check something real quick, ladies and gentlemen.
It wouldn't put the card down.
All right. Okay. All right, ladies and gentlemen. So I did just look at it, and that is absolutely 100% accurate about your quiz tomorrow. So you're going to have, you will not have to make a graph, okay? But you need to tell me what all graphs show. You need to tell me what kind of relationships are shown in a graph. So if it's a constant relationship, what would that look like? If it's an inverse relationship, what would that look like? If it's a direct relationship, what would that look like? Okay? So all of those things, okay? Jerry, you're taking a picture of a computer screen.
I know.
Okay, good. Put away your phone though, please. Okay? Thank you. So those are the things that are going to be on there. And the basics of kinetic and potential energy, which is what we have covered thus far. In other words, what does it mean if something has kinetic energy? What does it mean if it has potential? What are the factors that affect it? So what we did in that activity yesterday, that is the stuff that will be on the quiz tomorrow. Okay? So just so you know. So with that, that leads us into our question of the day. Give me an example of something with either kinetic or potential energy.
Did we do that yesterday?
Mm-hmm.
We did. So this is a good way to review for what we learned yesterday. So give me an example of something that has kinetic energy or something that has potential.
Booster.
Okay, why?
Because it has a lot of height.
So which one does it have?
Position.
Potential.
Potential.
What did you say?
Okay. Position. He's right. Position is one of the 3 ways that you can have potential energy. But what we were looking for was potential energy. Good. Okay. Give me an example of something with kinetic energy.
A car driving.
What?
A car driving.
A car driving. Why the clock?
Because it's in motion.
Well, what is in motion? Because that clock isn't moving on that wall.
Second.
Okay. So we have to be careful. Okay. And I'm trying not to be picky here and I'm trying not to be a jerk. But when you name an object, sometimes you name an object and people can look at it differently. So if you look at the overall clock, I would say, no, it's not moving. If you're talking about the hands on the clock, yes. Leaf, you said a what?
Car driving.
A car driving. Okay, good. If you say a car, does a car have kinetic energy? Sometimes, correct. So we need to be a little bit more specific. Now you say a car driving, that means it's moving. Yes, that has kinetic energy then. Okay? So again, people will say, well, an airplane has kinetic energy. Not if it's sitting on the ground not doing anything. Okay? So again, we need to clarify those things. Jay, give me another example of something with kinetic energy. Okay? How? Okay. That is actually an example of not kinetic, but of potential. And good, because that is another kind of potential energy. The examples that we gave you yesterday and the little activity that we did in class was all based on energy of position. So if we hold something here, here, and here and drop it, when does it have more potential energy? At lower, medium, or high? We also did it with a light object, a medium object, and a heavy object. Now that all covers potential energy, but that only covers potential energy based on position. Jen talked about pulling a bowl back. That is potential energy based on deformation, meaning pulling the strings on the bow, loading it up, getting it ready to be released. Another example of potential energy, but a different way of looking at it. So our formula for mass, gravity, and height really wouldn't apply for that, but it is still potential energy. Can somebody give me an example of the third type of potential energy for chemical bonds? Striking a match. Okay, what else?
Gas in the car.
Gasoline in the car. What else? A bomb.
Oh.
More, come on.
Flint.
What?
Flint and steel.
Okay, flint and steel. What?
Bullet.
Okay, can have potential energy. The gas inside there could burn, causing the bullet to actually leave the gun. Yes, okay, great, good. What else? How about what's in front of you right now? Okay, what's the energy source for it? Battery right now, we can plug them in and recharge the battery, but the battery right now, okay? Come on, please put away your phone. Thank you. Okay? So a battery is also an example of chemical energy, waiting to be stored, waiting to be used at some point. Okay? By the way, you want to make a lot of money, ladies and gentlemen? You want to become very rich? Here's the thing, and I only want 10% for the idea. Invent a battery that can last for a week in your cell phone without dying. If you could invent a battery that could go a whole week without needing to be charged, you could make a ton of money, ladies and gentlemen. Ton of money. Okay? Because the one thing that everybody hates about cell phone batteries and about batteries in a computer is they die quickly. Imagine if your battery on your phone didn't die for a week, if you only had to charge it once a week. Okay? By the way, the battery's got to be small, got to be powerful, got to be lightweight. So you can't take a car battery and put it into a cell phone.
I can't imagine how bulky the battery would have to be.
Go back and look at the first cell phones that were ever created. Okay? My wife had one that was a bag phone. You guys probably don't even know what that is. But the phone was actually about yay big, and it was in a bag because you needed that much space for the battery. So there's lots of ways of looking at kinetic, and there's lots of ways of looking at potential. And that's what we are going to do today, ladies and gentlemen. But also, yesterday at the end of the hour, we said that potential energy and kinetic energy depend on some things. What are the two things, bless you, that kinetic energy depends on? The mass. The velocity and the mass. And Cynthia said it best. Most of this is common sense. You're absolutely correct. Okay? Absolutely correct. Okay? If an object is moving very slowly at you, it's probably not going to have a lot of energy if it hits you. Now, how could a slow-moving object still have a lot of kinetic energy? What do you mean? If it has a lot of mass. So if you have a big dump truck, even if it's moving slowly at you and it hits you, it's probably going to hurt, correct? Okay? So you can have not a lot of velocity and still bring a lot of kinetic energy because you can have a lot of mass. How can you have a lot of kinetic energy if you don't have a lot of mass? With a lot of velocity. With a lot of velocity. Okay? Now, what's that?
Don't get hit in the face with the golf.
Don't get hit in the face with a golf ball. I wouldn't want to get hit in the face with a ping pong ball either. That would hurt, but it would hurt less than being hit in the face with a golf ball. Why? Golf ball has more mass. Okay? Two objects, same speed. The one with more mass is going to hurt more, ladies and gentlemen. Okay? So mass and velocity both affect kinetic energy. What are the three things that actually affect potential, one of which we cannot change? Gravity is the one we cannot change. Height and mass are, though. Okay? So if one of those boxes were to fall off the shelf and hit Najma on the head, she would be hoping it's one of the empty boxes. Why? Gonna hurt a lot less than if it's one of the full boxes up there. Okay? You're praying it's one of the full boxes?
Yeah.
You are mean.
Just a little.
Only to Nashville.
Oh, okay. Then it's okay.
Just a little.
All right. All right. Then it's okay.
I don't like it.
Okay,
Hello, sir.
It's a Thursday.
So it's my favorite day.
Thursday's your favorite day? Why?
Yeah, it's Thursday.
Thursday's literally.
Oh, because it's Thursday, it's your favorite day.
Don't say orange because Thursday's green. So
Thursday's
I don't know if I'd call Thursday green.
red.
I agree with red.
Thursday's
I
red.
agree with red because red's
Well, I wouldn't agree with the green. I don't know about.
I would
green.
agree.
Wednesday's green.
Can anyone tell me what the heck they're talking about? And don't say colors and days of the week.
Okay, buddy.
I think Monday's green.
Mondays.
Ugh.
Wednesday's is pink.
No, Monday's
Wednesdays are pink. I don't know
But
about
it's
that.
funny. On Wednesdays we were pink.
Yeah, that would make it Wednesdays are pink.
And then Friday's just
Friday's
black.
like,
Black.
Oh, God.
you're wrong with that.
Why?
Okay, moving on along to something that kind of matters.
Tuesdays are black.
All right, this is where we left off yesterday. Open up your computers and get to this, ladies and gentlemen.
One of the days has to be black.
No.
No.
No, it doesn't. Just because you want it to doesn't mean it has to be.
No.
Well, you got a problem with black?
One of the-
Yes, we do. Now knock it off. Let's go. Open your computers and get to this slide.
one of the-
We left you yesterday, ladies
Let's
and
not go
gentlemen,
there.
talking about this.
I want to go right now.
Talking about kinetic energy. And on the two slides, we said that if you increase the velocity of an object, you are going to increase the kinetic energy. If you increase the mass of an object, you are going to increase the kinetic energy. Did we get through the potential energy ones?
Yeah.
Both of them?
No.
No.
Okay, so we did get through this one, though. If the mass of the object increases, what happens to its potential energy?
And then what did you do?
You're wrong.
If the mass of an object increases, what happens to its potential energy?
It increases.
Increases. Okay. Jacqueline, there are 4 water containers in the room on the shelves in the back. Take a look at them. Okay? There, 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 and there. Which one has the most potential energy? Why? So? Thank you. What you have just done is found an application of the knowledge that you probably already had, but again, good job. Because it's not just about saying this, okay. You have to look at them, see which one has the most water in it, apply what we learned, which is if it has more mass, it's going to have more potential energy. Now you are assuming that they are also all at the same what? Same level or the same height, which is a safe assumption looking at the cabinets in the room. So when we have the heights being equal, now potential energy is only dependent on the mass. The one that has the most mass, most potential energy. Now, again, which one would have the least amount of potential energy, Daniela, when you look around the room? That one over there had the most. Which one has the least? The one back there has the least amount of water in it. So again, if the most amount of water is the heaviest because it has the most mass, the least amount of water is going to be the one with the least amount of potential energy. What kind of relationship? This is a direct. Okay? This is a direct relationship, ladies and gentlemen. Questions? All right. Now, let's make an assumption here, and assumptions aren't often good to make. But when you look in the back of the room, do you see all the bottles with the blue lids? Okay? All of the wash bottles that are like this with the blue lids in the back of the room.
Yeah.
Let's assume, even though it may or may not be true, that all of them have the same amount of water in them. Exact same amount in every one. Jin, which one has the most potential energy?
What, you said all of them?
They all have the same amount of water. All of the blue ones, any of the blue ones that you look at in the back, have the same amount of water in them. Which one has the most potential energy?
Wouldn't they all be the same?
Would they? Leaf, you're shaking your head no.
It'd be the one on the little center
Yeah,
island.
the one in the middle.
Why?
Because it's higher up.
You missed that one, maybe, Jen.
I'm blind.
Oh, no, that's okay. The one in the center island is just a little bit higher than all of the others, which means it will have the most potential energy. Now look very carefully. In the back, which ones have the least? Just slightly less than the others. Again, we're assuming they all have the same mass.
I don't know. I can't see it.
Anybody?
Close to the edge.
They would fall from the same height whether they were close to the edge or in the middle, though. But, all right, at least that's a good effort. Which one? What should you be looking for?
Oh, move slower than the rest.
Got it? No? Thought you did.
Wait, they're in the back.
There's two of them in the back that have a
Those
little.
ones?
Why?
Because they're lower down.
That one lab station right there, ladies and gentlemen,
Oh, yeah.
is a little bit lower than every other one of the lab stations in the back.
Save it.
I thought you had it, Brian.
Oh, I couldn't see.
I thought you had it. You looked over there and I thought you had it. Okay? Any idea why that station's lower?
Oh, they built it.
Because,
Why did they build it that way?
did they raise the floors in here?
No, for the same reason that there's an opening underneath it in the back
It's
there.
for
It was added later.
Nope,
wheelchairs.
it's wheelchair accessible.
Oh.
You have to have a handicapped station in each room. So that is the station where it is handicapped, so because the person may be in a wheelchair, they lower the table a little bit for them. Make it easier for them to work with. That is the one, though, where those two bottles on there would have the least amount of potential energy. Why? They have the lowest height. So again, the higher the object, the more potential energy it has. The lower the object, the less potential energy it has. What kind of a relationship? Direct. Direct relationship. Okay? So when we think about potential and kinetic energy, you have to think about those two factors. Now, which one would have more potential energy? Okay? A heavier object at a lower height or a lighter object at a taller height?
Depends on the ratio.
Correct. We cannot tell that. That is something we cannot tell. That is why in science we like to limit the variables. The heavier object at a lower height could have more potential energy than a lighter object at a taller height because we have nothing the same to compare them with.
How much heavier?
It depends on how much heavier one is. It depends on how much higher one is. Okay? Now, granted, you could calculate it. We gave you a formula. You could calculate it. I won't give you those type of questions, though. Okay? But again, when two things are equal, we can make a comparison. When their mass is equal, we can determine which object in the room has more potential energy by which one is higher up. But only if their masses are equal. And if their heights are equal, we can determine which one has more potential energy by which one is heavier. Keep that in mind, because here's our first question. Our famous CRC handbook, ladies and gentlemen. These ones that you like to drop on each other yesterday.
That did really break my head.
Tell me about its kinetic or potential energy.
It's gonna be gone out, and it's gonna be gone in like 30 minutes.
Najma, what?
Is there anything about it?
What can you tell me about its kinetic or its potential energy? Either one.
It's got a lot of kinetic.
What?
It's got a lot of kinetic energy.
It had
I was like,
when you
oh.
dropped it.
I'm not asking about when I'm
Like
dropped
right
it. I'm
now.
asking about right now.
At this exact moment,
At this exact moment, what do we know about its kinetic energy? Hello there, sir.
it just starts.
So what can you tell? Be careful, don't kick the book. Oh my gosh, you almost kicked the book.
None of either. So it has no kinetic.
Okay. And it has no what?
None of either.
Why?
Because it's still and on the floor.
Okay. The definition for something to have kinetic energy is it must be what?
Moving.
Is that moving? No. The definition to have potential energy is it has to be what? Able to
Able to.
fall.
Yeah.
Can it go any lower? Now again,
Without the
If the
floor.
floor falls
Without
in,
the
Yeah,
floor.
without the floor
falls
falling
in,
in.
we all fall in with it.
Can't go any lower, correct? No kinetic, no potential. Right? All agree?
Yeah.
Okay. But yet, I will have a student every year who says they can prove that that book sitting on the floor has both kinetic and potential energy.
What if it has a bomb?
It doesn't.
What if it has a bomb?
I know it has potential.
It's actually
It can have potential without having a bomb in it. Someone explain to me how that book has kinetic and potential energy right now.
That's really good.
Is it breathing?
No,
That
it's a
one?
book.
Oh,
It's
darn.
not breathing. I'm not tricking you that way.
Just yoking.
How can it have kinetic and potential when it's sitting there on the floor not moving?
So I can take it.
The electrons, they're moving.
What?
The atoms,
Yeah.
the particles are,
Particles.
are like going
The
around.
electrons and the neutrons.
Ridley,
They're moving.
What?
you're absolutely correct.
Oh, when I say
I
that,
told y'all.
Well, you talked about the electrons. She talked about the whole atoms.
I
Yeah,
said the electrons.
Yeah,
and
that's
neutrons
true.
and-
You did.
No,
You
you're
did.
wrong.
I'm basically smarter.
Oh, okay.
If you wanted to make a case, you could claim that this book has kinetic energy because the particles that make it up are moving around. Okay, Christian? Will you give it? Thank you, sir.
Giant.
Okay? So the particles inside the book are moving around. Okay? That is kinetic energy. Okay, good. Now explain to me how it has potential.
Declination.
No. There, you
No.
cannot deform that one.
No.
Because I can
I
light
put
it on
in
fire.
pages.
I could light it on
I
fire.
could explode
What?
it.
You are 2 for 2 today. You could do what to it again?
Oh, right.
Fire?
Could light it on
To
fire.
explode it, you know.
You could burn the book.
You could eat
But-
There is potential
but-
energy stored in the pages of that book in the chemical bonds holding the paper together.
The one time I actually saved
You
something
can
like that.
actually burn the book and get potential energy out of it.
You know,
So you remember your clock a little while ago at the start of the class?
Well, that's actually-
That was wrong.
explode it.
Okay, your clock example?
Yeah.
It all depends on how you're looking at something. If you're looking at the book overall, no kinetic, no potential. If you're looking at the particles that make it up, has kinetic. If you're looking at the fact that you could burn the book, it has potential. Okay?
Yeah, everything has kinetic energy because the earth is spinning.
Very good. That was about where we were going to go next. Which is somebody will say, well, Mr. Wren, that book is still moving. What do you mean it's still moving? Well, the earth is spinning on its axis, flying through space, moving all the time. Okay. Point of reference. Depends on what you're looking at. Example, car. Car doesn't have kinetic energy. The car moving down the road does. So you need to be specific if you're going to give examples, ladies and gentlemen. Very good, very good, very good. Nice job. Okay, so now think about this. An elephant and a mouse run a race. They tie.
Wow.
So while they're running the race, from the start line to the end line, they end up tied. How do their kinetic energies compare?
One's got more.
You tell me.
Well, the elephant, because he weighs more.
Okay.
But the mouse is able to move faster.
They're probably, wouldn't they be the same
it's
if
got
they
big
tied?
legs, too.
Wouldn't their what be the same?
Kinetic energy.
So you're saying their kinetic energy is the same because they end up tied.
Yeah, because then the elephant will be moving slower, but it's got more mass, and then the mouse is going light speed.
You're missing something in this question, ladies and gentlemen. You're missing
Wait,
something
what was
in
the
this
Aren't they
question?
running
question.
at the same speed if they tie?
What if it-
Thank you.
So then
The only way you finish a race tied with somebody is if what?
Same speed.
You go the same distance in the same amount of time, which means you have the same speed. So now these two objects have the same speed. What do we now know about their kinetic energy? Why?
Because it has more mass.
The elephant has more because it has more mass. But only because they're moving at the
Same speed.
same speed. They end up tied in the race. They don't end up with the same kinetic energy. Oh, wait. Look at our next question. An NFL lineman and a baby run a race, and they finish the race with the same kinetic energy. Who wins?
They tie.
Nope.
Oh,
Well, if they finish with the same connection.
I'm gonna say the baby.
Yeah. If you're
Well, good. We've limited down to the three options. They tied, the lineman, and the baby. Okay, so stop for a minute. Think about this. Kinetic energy depends on what two things? Well, that makes up for speed, velocity, and mass. So what is definitely different about these two? Mass. Which one is bigger? The NFL lineman.
Might be a big baby.
Nah, the
So
baby-
now think about this. Well, yeah, that would be a big baby. Okay? So now think about this. Two objects that have different masses have the same kinetic energy. So one of them, now if they were moving at the exact same speed, which one would have more kinetic energy? The lineman, just like the question above. The elephant has more kinetic energy than the mouse because they're moving at the same speed, right? Do they have to be moving at the same speed here? No, because it says their kinetic energy is the same.
So the baby's like flying.
Why?
'Cause
Well, if he's-
he has to
he's a
make
lot
up for
lighter.
the loss of mass with the speed.
Thank you. So if one object is heavier than another, the object that is lighter to have the same kinetic energy as a heavier object has to be moving how?
Faster.
Faster. Has to be moving faster. Good. Okay. Now stop for a minute. Think about the air in this room. What is the air in this room made up of? Particles. What particles? Oxygen and nitrogen. Oxygen and nitrogen. Are oxygen atoms and nitrogen atoms the same mass? No, they are not. No, they are not. So, the air in this room, though, is all at the same what? Temperature. Now, hold on a minute because you're right, Levi. You are. I don't know if any of you remember your physical science. What? You never
Yes,
had
we
physical
did.
science?
In like 6th grade.
We had it in like 7th grade.
You didn't have it here in 9th grade?
No.
You weren't lucky enough to have me as a
Science in 8th grade.
There is someone who had me as a physical science teacher in this class who was probably, maybe not taught this. Did you have me for the chemistry or the physics part? Okay, there was one year where I had to teach the physics part. And in the physics part, we learned about the difference between heat and temperature. Temperature is a measure of the average kinetic energy in matter. Average kinetic energy in matter. So therefore, this room is all at the same what? Temperature. So therefore, everything in the room has the same what? Kinetic energy. What are the exceptions to the things in the room that do not have the same kinetic energy? What things in this room would not have the same kinetic energy as other objects? Why? Nope, nope, nope. You're close though. You are right about us. What about us makes us not have the same kinetic energy as this tabletop?
Because we move ourselves.
Cynthia, feel the desk seat next to you.
State of matter.
Put your hand on it, feel how warm it is. Now, feel how warm the seat that you're sitting on is.
Our body temperature.
What about your body temperature?
98.7.
Which is what?
Temperature.
Higher than room temperature.
Oh,
So you and I
That too.
have more kinetic energy than the air in this room. What else?
This,
What else has more kinetic energy than the air in the room?
that thing.
That thing.
I
What?
forgot what it's called.
Projector.
The projector.
Thank you.
It's that-
Why?
Because the
It
lens
makes
heats
heat.
Because it generates heat when it projects an image.
up. The light bulb.
when it
The
works.
light bulbs. What else? What? Your computers and such. Computers, cell phones, things like that. Electronic devices. My computer, all this electronics up here.
I was gonna say
when you use electronics, they generate heat. They're warmer than the room temperature. What are you pointing at?
I was pointing at the pencil sharpener.
Okay, but the pencil sharpener hasn't been used in a while.
Aggravating.
So my guess would be right now it's probably pretty close to room temperature. Okay, only because it hasn't been used. Electronics that are not on, the hot plates in the back, are that. Electronics that you're using, they are going to be warmer. Okay? All right. So everything in this room is at the same average kinetic energy. Does that mean the particles in everything in this room are moving at the same speed? Why not?
Some things are more solid dense than others.
Density doesn't have anything to do with kinetic energy.
Have more
Thank you. Now, I understand what you're saying. Some things are more dense, which means there's more matter there. But what really matters is not the density. What really matters is the mass. And you're right. The mass of this table is not the same as the mass of the particles in the air. So therefore, which ones are moving faster?
It's not.
Why?
Well, let me- Yeah, it has to be.
So in reality, we could just say anything that is what?
The gas.
I don't care if it's a gas. There are some things that are gases that are very heavy gases.
Yeah.
What makes something move faster?
No.
All the kinetic energy is the same. So the temperature is the same. You got it just a minute ago when Jara said density. The mass. Again, I agree with you. The air particles in this room are lighter than the particles in this desk. Absolutely. But let's use the correct term. What matters to kinetic energy is mass and velocity. Those are the only two things. Now, density can affect mass. Don't get me wrong. Okay? But all we want to know is that it's the mass and the velocity that affect how much kinetic energy something has. Good. Okay. So 2 roller coasters are stopped at the top of the tallest hill at the exact same time. So it's a dueling racing roller coasters, 2 tracks side by side. They are stopped at the top of the hill. How is it possible that they not have the same potential energy?
More people in the car.
I don't care if one has more people in the cart. That is not the correct answer. But you're getting close to it because you're not using the correct terms that we just spent 5 minutes talking about. Thank you. More people doesn't necessarily mean more mass, does it? Right? You put 5 NFL linemen in one cart, you put 6 small children in the other. Does more people necessarily mean more mass? So let's use the correct terms. I understand what you were trying to get at, but again, we need to clarify. They could have different masses. Even though they are at the same height, if they have different masses, they have different potential energies. Okay? Different potential energies. How is it possible for a bowling ball and a golf ball to have the same potential energy? What? Ah!
Essential.
Potential energy.
More height.
Neither of them are moving.
The golf ball.
The golf ball has to have more height. The golf ball has to be higher above the ground than the bowling ball is. Okay? So just like the lineman and the baby could have the same kinetic energy, but the baby would have to be moving how compared to the lineman? Faster. Well, when we talk about potential energy, 2 objects that have different masses, well, one has to be higher than the other to make up for its lack of mass. Okay? It depends on those 2 things. Good. Questions? All right. All right. So give me an example and please be specific. Actually, take 2 minutes. Come up with an example on your slides and then I'm going to ask you for your example. Now please be specific. Think about this. To have kinetic energy, the object must be what? Moving. So when do you have no kinetic energy?
It's not moving.
When it's not moving. To have potential energy, the object needs to be what? Able to fall. That's what we're going with here. If you want to go with a different definition of potential, you can, but again, you need to be specific in your answer. To have no potential energy, the object cannot fall. So give me an example of each of these, please. Take a couple minutes and write one up. If you're sitting next to someone, you could confer with your neighbor.
You're
Depends on how you look at it.
Would that be, I just have a, when you're at the top, that would be potential, right? Potential energy.
The atom.
I mean, yeah.
Or the magnet.
Okay,
And then
why?
while it's moving, it's kinetic. Yeah.
Very good. Very good.
Mm.
Who'd you have for physical science?
You.
No, for the physics part.
You.
You hit me for the physics part? Did you?
For the first part?
For the part on motion and energy and things like that.
Actually, no,
Okay. That one can be before the other. So you can't say the first part and the second part because it's broken up into the chemistry and the physics part. So she did a good job.
I did that chemistry with you.
Yeah. See, I've always taught the chemistry part, but there was one year where I think it was probably 2 years ago where I had to teach the physics part so that another teacher could teach the chemistry part. So that's why I asked. Because normally it's Schunard or Bukowski or someone like that. All right, are we ready, ladies and gentlemen? All right. Yvonne Jasmine, pick any one of the four and give me your example.
Potential only, no kinetic boost.
Potential only, no kinetic. What'd you have? Okay, the poster's in the room. Good, perfect. All right. Brianna, Jacqueline, pick any one. No. What did I do? Oh, I'm sorry, Brenda. I think I've done that twice to you today, haven't I?
Yeah, you did.
I'm sorry. I'm sorry, Brenda. Brenda, Jacqueline, you can call me Mr. something else then for a while, okay?
Mr. Nass.
No! My gosh, no. Cynthia, I didn't call you the wrong name yet, so leave me alone, Nadia.
Yeah.
Okay, go ahead. I'm sorry, Brenda. Jacqueline, what do you got? Which one?
The first one, kinetic energy, I have no potential, a person walking.
Okay, I agree somewhat. Okay,
Only kind of falls.
what?
Only kind of.
No. Be careful. You're right. A person walking. But I'd like you to be a little more specific. Can someone help them out to guarantee that there is no potential energy there? Because I would say, what if you were walking across the footbridge over the East River?
So person on the ground. Like on the, like.
Person walking on the edge of a cliff.
If you shoot a book out of cannon, that is kinetic energy.
If you were
Okay, person walking on a level surface. A person walking across the classroom floor.
Yeah.
That doesn't
Again.
guarantee anything, you could still fall.
It's not about you falling. Okay? And again, I guess we need to clarify this because Jared brought this up yesterday. We talked about falling out of your desk. Okay, are you guys okay?
Yeah, they're fine.
Okay.
Because
So,
his example's wrong.
It's fine.
Hold on, we'll get to his example in a minute. So again, if you trip and fall, yes, technically the upper part of your body has potential energy, it's going to hit the ground. We're looking at the object as a whole. So if you're walking on the ground, we're assuming you can't go any lower, which is why you need to, in reality, somehow give me something that talks about being at the lowest point. Walking at the bottom of a valley. Why? You can't go any lower than that. Walking on the first floor of a building. You can't go any lower than that, okay? Again, walking is a great example of kinetic energy, but we need to make sure we're specific enough so that on your test when you take it, you're not accidentally giving me potential energy as a possibility as well. Okay? And as my college professor used to say, if a bicyclist rode by, he'd want to know that. That's meaning that I'm telling you that question is going to be on your test. You're going to have to do something like this. Okay? All right.
I have to give examples.
Yes, you have to give examples. Oh my gosh, if it kills you, I won't ever make you do it again. So now let's go to the one we were debating.
No, mine was later. Mine
Because-
kinetic and potential.
Okay,
Well,
which
he
is
said-
what?
I said if you shoot a book out of a cannon.
But he's implying just the action of shooting the book out of the cannon, not just having a book in the
No,
cannon.
I'm saying the book after it's been shot out of a cannon.
But
Then
it
wouldn't
just
that have all
you're
kinetics?
just
Slow
saying
down, slow
the
down.
action.
But that, no, I'm.
Unless you're saying a book sitting in a cannon.
Okay,
But the
but
book is not sitting.
wait.
It's
He's
flying.
describing. Wait, go back. Levi, which one are you describing again?
Kinetic and potential.
Okay. So you tell me, what does an object have to be doing to have both kinetic and potential?
Moving.
And above the ground. So an object shot out of a cannon, would it be moving above the ground?
Yes.
I don't trust that.
And it can be lit on fire.
Okay, but that would
Well,
be a
that
whole
doesn't
different
have
way you'd
anything to
have
do
to
with
tell
that.
it. Okay? Alright? So the
But
important
here's the
thing is
thing.
if you want to describe both kinetic and potential, give me another example of kinetic and potential. Christian, give me an example of something that flies through the air. A plane what? Has to be doing what though? Flying. A plane sitting on the ground would not have both, right? So a plane flying. What else? Give me something. Haley. A bird flying through the air. Give me something. Rocio.
Baseball moving. Throwing a baseball.
Okay, throwing a baseball through the air, because be careful. How could a baseball
Could be rolling on
have kinetic but no potential? Miro?
rolling on the ground.
If it were rolling on the ground. Okay? If it were rolling on the ground. So again, we have to talk about it being thrown in the air to somebody. Okay? Your plane has to be flying in the air. It could be falling to the ground in the air. The engine's failed and it's crashing. It's still got both kinetic and potential, at least for a little while. Because it is both moving and it is above the ground. Okay. What?
Then it might set on fire.
Correct. But again, we're getting into a different kind of potential. Daniela, can you give me one of your examples? What's that? Well, can you give me one that maybe we haven't? How about no kinetic and no potential? What'd you put for that one? You didn't get to that one? You don't have an example sitting next to you? You don't have an example sitting next to you? You don't have an example sitting next. You don't have to hide that. That's your charging block. Look down to your left. Further back. Down. What is that? Yeah, what's it doing?
Sitting on the ground.
Does it have kinetic energy? Is it moving? Can it fall any lower? Again, the overall object. Can it go any lower?
I guess not.
So then what does it have?
Nothing.
No kinetic, no potential. Again, we're not going to get into, okay, I got to lay it on its side so that less of it,
Stressing.
it's on the ground, it's not going any lower. Okay? On the ground, not going any lower.
With potential, are we only looking at falling?
Well, it is the easiest way to look at it. If you want to give me another example, no kinetic and potential energy. A cheeseburger sitting on a plate on the ground.
Yeah, because it's raising.
I was thinking-
Well, actually, you wouldn't even need to put it on the ground.
I was thinking.
A cheeseburger sitting on a plate.
Yeah.
Because either way, it's going to have potential.
Yeah.
Potential energy for you when you eat it, Potential energy because the plate is sitting on a table. But no kinetic, why?
Because it's not moving.
Okay. No kinetic and potential.
I don't think we're ready.
A bow pulled back with an arrow loaded in it.
Doesn't have potential.
It doesn't?
Deformation.
Also, if I'm holding it like this, think about it. The arrow can still what?
Fly.
How about fall to the ground?
Yeah, it's still fall.
Yeah.
As long as it's above, and it would have potential because of deforming the bow ready to fire. Does it have kinetic though? No, because it's not moving. Okay? The important thing we want to stress here, kinetic, moving. No kinetic, not moving. Again, potential, there are 3 ways of doing it, but the easiest way that we think of normally is height. Okay? Easiest way we think of normally is height. Okay? All right. So let's get into this, ladies and gentlemen. This is where we're getting into it. And the reason that we spent a bunch of time talking about kinetic and potential energy is because now we're going to relate it to something called KMT. KMT is kinetic molecular theory. What is a theory?
Educated.
No, it's a little bit more than that.
There was a definition
The,
for it,
the evidence supports it, but could be further.
but it could be changed.
Okay. A theory is something that the evidence supports. Absolutely correct. And it has been tested. And we get the same thing over and over again. But we're not 100% sure to where we can call it a law. Okay?
Get more evidence.
Gravity is a law. In other words, if I take an object and I drop it, I can measure how fast it is going to fall. And it doesn't matter what the object is. All objects fall at exactly the same speed. That's a law of gravity. Okay? You cannot deny that. It can be mathematically proven. Theories are the best explanation for all of the evidence we had. Now, an educated guess is just a hypothesis. Here's what I think is going to happen. A theory, we tested this and tested this and tested this, and this is the best we can do. However, maybe it's not 100% right. Now, there are 2 points to kinetic molecular theory, ladies and gentlemen, or KMT. And it is how we look at matter in chemistry. Point number 1, all matter is made up of tiny particles. Now, this part is indisputable. All matter is made up of tiny particles. What do we call them? Or molecules. There's a list of them right there, ladies and gentlemen. There are all of the different atoms known to man, including the ones that we have created. So on that periodic table up here, ladies and gentlemen, the first 92 elements are naturally occurring on Earth. The first 92 elements up to uranium are naturally occurring on Earth. From 93 to 118, we have created those in a laboratory somewhere. Okay.
Wow.
All right.
Wow.
Good. Okay? And those things make up everything around us. Those 92 things make up all the different things that you see around this room. So let me ask you this. Are there more atoms or are there more compounds? Compounds. Definitely. Otherwise, we'd be under, say, 236 different things. If it were just atoms and not compounds. Compounds are combinations of those things. Literally billions upon billions of compounds in the world. Okay? Those are the tiny particles that make things up. Your desk is actually made up of tiny particles. Your computer, your coffee cup, the plastic bag, your ID, everything around you, including you and I, is made up of tiny particles. Okay? That part is not the theory part. Now, what those particles are, that could be a theory. Now, we know there's atoms, we know there's compounds, but there's things that are smaller than the atom, which are what?
So,
Subatomic particles.
What are they?
yeah,
Protons, neutrons,
electrons.
electrons.
And there's actually evidence that there's still smaller particles than those out there.
Yeah.
That's the theory. Quarks. What?
Quarks, photons.
Well, actually, photons are bundles of light energy. They're not matter. Okay?
This strings.
Yeah, strings, like on a guitar. Yes, absolutely.
Yeah.
Okay, point number 2, and this is the part that's the theory. Those tiny particles are in constant motion. Those tiny particles are always moving. Which means they always have what? What? Kinetic energy. They always have kinetic energy. Now here's the theory part. What would happen if we stopped them from moving?
They die.
We don't know. We've never gotten matter that cold that we have stopped the particles from moving.
Okay, isn't that absolute zero?
That is absolute zero, yes. Okay? Never gotten matter that cold. We don't know exactly what happens. But we do know some weird things happen when we get close to absolute zero, when we cool things down. Okay? So that's the theory part of this still. Okay? But this is what chemistry is all about. These tiny particles that make things up. They are always moving. So right now, the particles in your desk are moving. Can we see them? No. Why?
They're so small.
They're so small. Okay? They're so small. Okay? I remember one time a teacher told me a story. They gave us these new hover cams, and the teacher was zooming in on their desk. And you know how sometimes pictures will get like pixelated? You know what I mean by that? Where it'll just have the little dots and things? And some kid goes, wow, are we looking at the atoms that make up your desk? No! You think these things have that good a zoom on them that you're going to look at the particles in your desk? Heck no. Okay? But it was a pretty good example because the pixels kind of moved around. Okay? They were tiny little particles. At least the kid had some science knowledge. Okay? So,
Whoa.
now in terms of this, in terms of kinetic energy, means matter always has kinetic energy. Always. Okay? So, this explains interactions between matter and energy. What's the temperature like today compared to the temperature like on Christmas? Colder. Now, out in front of East High School, we have a flagpole. What state of matter is it? Solid. Made up of particles. According to this, those particles are always moving. How are they moving today compared to the way they were on Christmas Day?
Nowhere.
Why?
Because it's colder.
Okay. So when it gets colder, the particles have less what? Less kinetic energy. Now, what can change about the particles in the flagpole that affects kinetic energy? What are the two things that affect kinetic energy?
Velocity and mass.
Velocity and mass. Let me rephrase that question. What about that flagpole particles cannot change that affects kinetic energy?
Oh, no, the gravity. There's no gravity's potential.
Gravity has nothing to do with it.
This is such a good thing.
Come on. Okay, this tabletop. Made up of particles.
Yeah.
They're moving.
Yeah.
They have kinetic energy. What can't I change about those particles? I can't change the mass.
Oh, yeah, no.
Once we know what the particles are, we cannot change the mass, right?
Yeah.
Okay, you can't make these particles heavier. You can't make them lighter. So what is the only way to change the kinetic energy of this table?
Velocity.
To make the particles move faster or slower. How do I get them to move slower?
Cooling.
Okay, we come here tomorrow, the heat's out in the building, it's 20 degrees colder, these particles are going to be moving slower. We come in, the heat goes crazy, it's 10 degrees warmer, they're going to be moving faster. The particle size cannot change, but its kinetic energy still can. Why? Because you could change how fast the particles are moving. Okay? You could change how fast the particles are moving. Now that's different than what we said a minute ago. Compare the particles in this table to the particles in the air. They're at the same temperature. But what's different about the particles in this table compared to the particles of oxygen and nitrogen in the air? Their mass is going to be different. Which one's going to be heavier probably? Particles in this table or the particles in oxygen? Table. So that means these particles are moving how compared to the particles of oxygen in the room?
Slower.
Slower. Heavier object has to be moving slower to have the same kinetic energy as a light object. Okay? Something has to be the same though. The kinetic energy has to be the same. The mass has to be the same, or the velocity has to be the same for us to make these comparisons. Okay? Something has to be the same. All right. So, real quickly, ladies and gentlemen, you have all seen this already. Okay? Solids have a definite shape and a definite volume. What that means, ladies and gentlemen, is this book is not going to change its shape just because I put it in the cabinet, just because I put it on the counter, just because I put it on the floor. Now, what happens all the time is somebody says, well, Mr. Brandt, I could take and I could break that stapler. Then it doesn't have a definite shape. Yes, it still has a definite shape. You have just changed it. Okay? You have just changed it, but still has a definite shape. Yes. Hurry. Liquids have a definite shape, but no definite, a definite volume, but no definite shape. Means they take up a certain amount of space, but liquids will do what?
Fit their container.
They will take the shape of their container. They will deform, they will move, all of those things, but more importantly, they will take the shape of their container. Okay? Gases have no definite shape and no definite volume. They will take the shape of their container and they will do what? And they will fill their container. Gases completely fill their container. And this is a good thing because if we walk into the back of the room, we do not start choking to death because of lack of oxygen. Hope not. Okay? Gases take the shape of their container, they completely fill it. As far as the motion goes, solid, vibrational, and slow. Liquids, semi-free, they can move around but are limited. They can't get completely free of each other. And they have a medium speed. Gases are completely free. They spread out and they move as far away from each other as they can. So in terms of energy, solids have what kind of energy compared to gases? Less. They have low energy. Liquids are medium. Gases are high. Why? Because gases move faster. The same particle as a solid, a liquid, and a gas has to have more energy as a gas because the particles are moving faster. Has to have less energy as a solid because they are moving slower. Questions? Okay, wonderful. Excellent. Phase changes real quick, ladies and gentlemen. Okay, what do we call going from a solid to a liquid? Melting. By the way, science also, chemistry also uses a special term, fusion. Okay? Fusion means melting. Okay? What do we call going from a liquid to a gas? Or boiling. Either one. The hard one, going from a solid to a gas, skipping the liquid state. Sublimation. Sublimation. Why are these all in red? Because they require the addition of heat. They require the addition of heat. The addition of heat, we use the term therm. Therm means heat. Endo means to put it in. Endo means inside. So you are going to be adding or putting heat into these things to get ice to melt and become liquid water. To get water to boil and become vaporous steam. Okay? Now, what do we call going from a liquid to a solid? Freezing. Actually, two other terms. Solidifying or crystallization. What do we call going from a gas to a liquid? Condensation. Where will you experience condensation?
Outside of your
On the outside of your drink on a warm summer day. Where will you experience it every morning, probably?
Walking inside.
Oh, not much dew out now.
or if you have a shower.
Could be, though, when you take a shower.
Yeah.
You get out, the mirrors fog up in there, that's the condensation on there. Okay? Maybe you have a good exhaust fan, maybe that doesn't happen. So, a gas back to a solid is called deposition. Frost that appears on your car window, deposition. Water vapor in the air goes directly to a solid on your car. Why are these all blue? You're taking away heat. You're taking away heat. Energy is being removed. Okay? Energy is being removed. Okay? We did what just now? No. Let's try this again. Turn the lights on.
Oh, you're doing
What did I now do? Took away the light. I didn't turn on the dark. You cannot turn on the dark, can you?
You done turned on the dark.
You can't turn on the dark. You cannot, ladies and gentlemen, add cold. You cannot add cold. What do actually? You take away heat. So if you're going to take a liquid and solidify it, you don't add cold, you take away heat. There is no way you can add cold. Okay? All right? All you can do is take away heat. Questions? Okay. So the last slide, I did it as a diagram. Here I gave you definitions for it. Okay? That's all I'm doing here is giving you definitions for it. Okay? So freezing and fusion or melting, process of going from a liquid to a solid or a solid to a liquid. By the way, these processes are what of each other? I want an easier term. Opposites, thank you. Stop, opposites, thank you. Inverse, you're trying to get a little too technical on me. I'm a simple person, let's go with opposites. Okay? These processes are what of each other? Opposites and opposites. Now, by the way, the definition or the difference between evaporation and vaporization. Evaporation is a process that happens all the time to water. It goes from a liquid to a gas only at the liquid surface. You do not have to heat it up. You do not have to add anything. It just naturally occurs. To get water to boil, you need to do what? Heat it up. Add energy. Okay? Add energy. So evaporation and boiling are slightly different, ladies and gentlemen. Slightly different. Questions? Please remember, some of the processes are exothermic, meaning you have to take and remove energy. Some are endothermic, meaning you have to put energy in. Questions? Let's see what's on the next slide. All right, this will be the last slide we get through today. Differences between evaporation and boiling. Evaporation changes from a liquid to a gas at the liquid surface. No energy is needed, happens only at the surface, and only a few particles can do this. And I will give you time now to get caught up. So evaporation happens at the surface. Where does boiling happen? It does happen everywhere throughout a liquid. But where does it actually start?
At like the
base.
yeah.
Why the base? Why the bottom?
Or wherever the heat source is.
Yeah.
Thank you.
That's normal.
Whatever is,
Think about
which you are correct. Normally, if you're on a hot plate on a stove, the bottom, which is why the bubbles start there and do what? Work their way up. So yes, it's a change from a liquid to a gas, not necessarily at the liquid surface, actually at closest to whatever the heat source is. Boiling, what do you have to add? You have to add energy. Energy has to be added.
To take away the cold.
You you take away the cold. You have less cold there. Okay? You go home at night and turn on the dark in your bedroom when you go to bed too. I understand. It happens closest to the heat source for boiling. Okay? And then you're right, once you get it up to a hotter temperature, it'll happen throughout the liquid. Evaporation only happens at the surface. And only a few particles can evaporate. Not all. What would happen if all particles evaporated?
Then we wouldn't have nothing.
We wouldn't have any liquid water on our planet. All right? We wouldn't have any liquid water on our planet. Okay? Boiling, any particle anywhere can do it because once you add enough heat to it, it will boil.
That's kind of scary.
What's that?
I think that anything could boil.
Well, let me rephrase that. Not every substance can boil, right?
Yeah.
Can you melt that iron pipe on the wall?
Yeah.
Could you boil it?
You could boil
I mean,
the
yeah.
liquid that.
You can boil iron. You can take liquid iron and you can actually boil it.
That's weird.
Can you boil this wooden desk? Can you melt this wooden desk? What will happen instead? It will burn. So not everything can go through the states of matter. Some things, the bonds are too strong that instead of becoming a liquid or a gas, they will simply break apart and burn. You'll decompose it. Okay? Good. Questions, ladies and gentlemen?
All of us can do that.
All right. Excellent. Wonderful.
You wanna try that?
So now let's talk about what day is what color or whatever. No? We've had that discussion. We're done.
Monday is green. We agreed on that.
Why is Monday green? Because it's a go?